Today we are going to do some revision on the heat transfer topic. As a revision, radiation is the means of transferring energy such as heat through the space. More specifically, radiative heat transfer occurs through electromagnetic radiation. When heat flows from hot to cold through a physical medium, we call it conduction. And convection transfers heat to a fluid medium flowing past a heat source. Convection relies on gravity or other force to push the fluid past the heat source. The temperature of a spacecraft depends on the balance between the heat received from external and internal source and the heat radiated to space. In order to control spacecraft temperatures, it is necessary to control the heat absorbed and the heat radiated, or both. Next, the thermal control elements. There are two types of thermal control method, passive and active. Passive thermal control is an open-loop means of controlling the spacecraft temperature by carefully designing the entire system to regulate heat input and output and creating convenient heat conduction path. Meanwhile, active thermal control employs working fluid, heater, pump, and other devices to move and eject heat. The most famous used passive thermal control is multi-layer insulation, or MLI. MLI consists of alternating sheets of polymer material such as mylar or Kapton and often looks like gold foil. We can apply MLI or simply mylar or Kapton adhesive tape to surface to vary the amount of heat absorbed by different areas and insulate the subsystem underneath. This is an example how MLI is applied on the spacecraft. Beside gold color, there is also a black MLI and white MLI. The next passive thermal control example is surface finish. Surface finish are available covering for a wide range of absorbance per emittance value. Paints generally consist of a binder that is transparent to visible light and a filler material that gives its color. So there are four basic categories for thermal control surface: a solar reflector, solar absorber, flat reflector, and flat absorber. This is a property of common thermal surface finish. When we decide to use the surface finish, we rely on the absorptance and emittance value. And there's another example of the surface finish. Vapor deposit thin gold film at astronaut helmet to control the heat. And then thermal control mirror reduce satellite operating temperature and diurnal temperature variation, as well as aluminized mylar at lunar mission spacecraft. The next passive thermal control is radiator. So the most effective long-term method for ejecting heat is by radiation. To radiate heat, we must design special surface areas on the spacecraft with low absorptivity and very high emissivity. These special areas then readily emit any heat concentrated near them. These surfaces are called radiators, and the radiating power of a radiator is a strong function of temperature and rely on the Stephen-Boltzmann constant, or alpha. This is the figures show the radiator energy balance and the surface finish determine the absorptivity as well as emissivity of the material. This is an example where radiator is applied on the spacecraft. And another example of the passive thermal control is heat switch, also known as thermal switch. The heat switch are devices that switch as needed between role as good thermal conductor and good thermal insulators. When one is installed in the heat conduction path between a warm, heat-producing component and a heat sink, the change in thermal conductance it affords can control the temperature of the component. Heat switch can passively control the temperature of warm electronic or instrumentation without the use of thermostat and heaters, thereby reducing power requirement as well as the need for heater control circuitry and software. This is an example where we apply the heat switch, and the heat switch component which is consists in the thin plate heat switch or pedestal heat switch. And thermoelectric cooler, this the famous one known as TEC, a miniature solid state heat pump capable of providing localized cooling to devices that require cold temperature for proper operation. TEC provide cooling via the Peltier effect, which is the cooling that results from the passage of an electric current through a junction formed by dissimilar metals. The simplest TEC consists of two semiconductors, one p-type and one n-type, connected by a metallic conductor as depicted schematically in the figures. This is an example of thermoelectric cooler known as Peltier module. And this is a conventional heat pipe. Heat pipe is a device that transfers heat in the form of the latent heat vaporization using volatile working fluid that is circulated by capillary action in a porous wick structure. They are capable of large heat transport rates at very low temperature gradient. An example of the active thermal control is heater. Heater is the simplest and most obvious active thermal control device. Heater may be in the form of compact metal-mounted resistor, metal coaxial cable in which the heating element forms the core of the cable or adhesive sheet. Another example of active thermal control is flowers. Flowers are active thermal control elements that have been used in different forms on numerous spacecraft. While most commonly placed over external radiator, flower may also be used to modulate heat transfer between internal spacecraft surface or from internal surface directly to space through opening in the spacecraft wall. This is an example where we apply lower in the spacecraft. Another example of active thermal control is phase change material. The use of phase change material or PCM for thermal control is not new. Consider the use of the ice box to store perishable food before the development of efficient, inexpensive, and active refrigeration system. The numerous electrical components on a spacecraft present thermal control challenge. High power dissipating component must be prevented from overheating without the earthbound benefit of free convection to the air or conduction to a cold plate. Conversely, components that are only activated occasionally must be prevented from cooling to temperature below operational level, and the lack of atmosphere preclude normal convective method of thermal control. Such components present an ideal application for PCM thermal control. And this is the schematic diagram of how PCM is actually work.